with Projective Geometry, right? So anyone here has an idea of what happens when I'm seeing all of you? What actually happens? How do I see you, and how do I understand who is sitting in front of me? What are the things in front of me? Any idea? So people with computer experience, please keep quiet. People who don't have computer experience, please do talk.
Basically, an inverted image falls on the retina,
Okay.
and then there's a nerve that's connected to the brain, and it passes on the information. If it knows already who you are, it will instantly recognize you.
Okay.
That's how you basically identify.
But before that happens, what happens before that? How does what rays falls on your eye?
Like the light that reflects off that
Object, right?
Yeah.
Okay, so the light reflects on an object, and then that falls through my retina into my inside my eye, and there it forms a inverted image, which is then so sort of, right? And then which again converts to electrical signals, which are then sent into your visual cortex, where your visual the processing of visual information. So I mean, when I see someone, like what actually happens? People experience people, or neural network experience people, right? But what happens? How does the detection of a person happens? So you don't have any idea this is good.
I have.
So the more interactive it is, right? So. I guess.
When we see an object, it's more like our eyes sense a little bit projection of this to.
Right. But now, how does brain figure out? It's not like you have one little thing that converts into an image, which again gets converted into another image, which again gets converted into another image. When does that brain go saying, okay, this is Sumod standing in front of the bokeh, for example? So in a sense, okay, so we have synapses which connects. So essentially, we're neurons. So this is the channel signaling to the neurons. So that processing happens in the visual cortex, which then there's a whole bunch of things there to understand things about us, and that again passes a signal. Right? But at the end of the day, everything in our brain is a signal. I can go and maybe invoke a particular neuron in his brain, and he will feel as though he saw me. Right? Or a few set of neurons, I go and activate, and he'll see as though he sees me. Or I can activate a neuron in my brain that will make me feel like a gaze to her. Or I can activate a neuron in my brain and it can increase empathy. Or I can activate a neuron and it can make me feel as though I'm standing outside of my door and seeing my door. These all are known phenomena. So at the end of the day, all of them are regulatory signals. Right? I mean, our all consciousness, everything we think about, what I tell you, what you believe about yourself, about your parents, all those are regulatory signals at the end of the day stored in your brain as synaptic waves. And there are a lot of interesting phenomena because of this, which I find very interesting. Neuroscience, for example, one is this particular case, this case might be pretty low because so many potentially. So there's an interesting case where this guy, so he had an accident, and then his parents visit him. He says that my parents are fraud. They are not real. So it's not real parents. When they come to him on phone, he has no problem. We will say that they are real parents. Any guesses why what's happening? No, they never tell.
I mean, like, they call this the imposter syndrome.
So if you know what exactly this is, why did that happen? Why did the imposter syndrome happen? Any guesses?
Vision or section of the brain gets damaged.
Okay. How? But he's saying this is my parents, but they are imposters. Right? Okay, what happens?
The particular nuance which is used for getting experience where in this part, speech part,
So exactly. Okay, so essentially that what happened is you have multiple parts of the brain. One is called the emotional cortex, one is the visual cortex, and the auditory cortex. Now, for visual cortex, there's a connection to your emotional cortex, and there's a connection also to your auditory cortex to your emotional cortex. Now, in this particular person, the connection between his visual cortex to the emotional cortex is open. So when he sees his parents, all the emotions he feels about his parents are not involved. So he feels that I'm seeing them, I recognize them as my parents, but I don't have any signal being created, then that should mean that they are imposters. And so it's just our own brain coming with reasons to stuff. So anyway, so it's a very fascinating, the whole area of consideration is largely about understanding, taking biological insights and then using computers to model and using mathematics is a very powerful tool to represent and model all of these processes. And projective geometry is very, very useful, very, very powerful model to do. And applications of that include things like, so one example is, so I want to do what we call a projective distortion. So here, Audrey Hepburn's picture, I want to put it onto this, into this image where I sort of want to put it in that region, is what I want to do. And now the question is, how do I automatically, given those 4 points, how do I automatically convert this image such that it will fit there correctly? What is the transformation I do? Right? Or I can do the inverse of that, which is I can, for example, those 2 doors I have, I want to view them as though I'm looking straight ahead of them. How do I get it? What kind?
First of all, the second part you can do perspective transform or coordination point, and then you can project the image over there and take it back to the usual place.
Right, you don't need to do that. You can make a more simpler solution. So, okay. So essentially, you're trying to work with then so we'll say what that is. So this is an example of something you can do once you know what it is. Okay. Another example, say weight switching is another example where you're taking a panorama of many images. But now, how do you put them all together? And many of them, it will not be like I take one exact picture of this touch, another picture here of exactly, and I can easily time them. It might be that I took one picture at one angle, and the side picture angle. They all might be overlapping, but they're not exactly overlapping. Very precise. Now, given these images, how do I stitch them automatically and create a one single panorama? Okay. Can anyone think of a panorama that we all use every day? No, not algorithm. You're telling me algorithm. What is that? I think phone won't do that. Okay. Another one that you see as panoramas. Another application that you see as panoramas.
Yeah, this is
No. A computation application that is doing panorama. And we all of us have checked that out. Not, I don't really check that. Everyone here have not checked that out. Okay?
yes.
VR could be one application, but something not, VR maybe not everyone is done, right? There's one thing you all have seen.
Maybe what we see is
Yeah, that is his answer. So Google Street View, right, for example, right? That's actually a panorama, right? The 360-degree panorama, not just a few angle, and it's not just 360, it's a full spherical panorama, right? That you can see in all 360 degrees, right? And what do? So they take at one point you take 360-degree panorama, then you move on a few steps ahead, take one more panorama, and then keep doing that again. And then what you provide? You allow the user to press a button to move to those points that you take in the panoramas. Okay? So you almost feel like you're walking through that space. Okay? And now common flow and other people are using it for example for selling houses. Okay? You can give a walkthrough to of your house without actually going to the without having someone to come to your house. Now there are more challenges, right? The challenges there are how do you ensure that the points at which you take these panoramas are such that you stitch after stitching from one panorama to the next panorama there is exact overlap, right? That you don't miss anything in between. And there are more complicated things. I mean, yeah. So you should make other assumptions about this. So that's another example of 3D Projective Geometry. So before this, another example would be iconics is another one where they use. So yeah, you can just use the feedback. So for example, so how many of you know other applications of 3D vision? Let's ask that. Like the document scan. Okay. How is document scanning?
There will be a perspective transform.
Okay.
That is like take it from any angle and then make it proper.
Right. So that's an example of what we already spoke about earlier. Right? Projective distortion. So I take a picture of an image from an angle like this. But after I take the image from this angle, I want to see the image just as though it's acting a top view of the image. Okay, what else? What other applications have you seen?
Drones.
Okay, what in drones?
Drones are trained to follow a particular trail of path.
Uh-huh.
And I think they use 3D SLAM for that.
Okay, what is SLAM?
Not much of an idea about it.
Simultaneous localization and mapping. Okay. What is that?
Means like the board doesn't know exactly where it is. So first of all, it is telling where it is, and at the same time, first of all, if you present a board over here, it has to come to know about the environment, and based on that environment, it will map again, and it will move a certain direction, and it will again localize the environment. So that's how it is finding the path.
So there are two things it wants to do. Right? You have a robot, okay, or a car driving on the road. Now it needs to figure out where I am first thing. Right? If I want to take any action, I need to know where I am. Okay? If I have to go ahead or I have to stop, I need to know where I am. That is called localization. Right? And the next one is what is called mapping. Right? As I move around, I want to keep a map of where I have been through and how I have moved. Okay? Simultaneous localization mapping means that as I am localizing, I map my environment as well and I keep moving. And that's a very good example of computer vision in action, okay? Wherein I'm actually at my robot as it moves. So one way of doing that is using initial measurement units like accelerometers, gyros, but they all have errors when you use them in situations. And computer vision has been used quite successfully along with these IMU units to localize and map very accurately. So, for example, driverless car from Google's Waymo and all, they use a combination of LiDAR, that is like laser pulses to get the net. There are maybe more experts in the room. So if you have more inputs in here, and along with the LiDAR, you also have vision sensors, which also provides information to localize where the car is. Now, so that is another application. Okay. So to understand for a robot or for a car where it is and to understand where it's moving as well. Because for example, you can use GPS, right? But why not use GPS? You probably use answers.
And simple app can be just curve surfaces scan.
What is that?
Like that, if you put a tag on your bottle for the security purpose or something like that, and then you want to do some kind of reset measurement, then you have to unfold it.
Right. You're on board and move any So any sort of methodology you need calibrating with the cameras in order to get it right. So another application. Okay.
But can you do in this reconstruction the precision measurements?
It depends on what assumptions you have usually, but you can to some degree. So it depends on different scenarios.
Depends on software or depends on the camera?
Depends on the scenario you are taking.
Application.
The application is what defines it. Other applications? Yeah.
This is what we have.
Augmented reality, right? How many of you know what's augmented reality? Some hands, some of you. Okay. So augmented reality, do you have any visuals? So augmented reality is essentially, so you have a camera that is looking at your world, and you want to augment virtual objects into your camera view, right? So essentially, I'm looking at maybe the scene, and I want to see how the scene would look like if I place a sofa here. Okay? So I will have a 3D model of the sofa created somehow, and then I want to know if I place a sofa here. I want to place. I'm looking through the camera now. Let's say, for example, I take the camera from here, and I'm seeing the camera live view, and I'm seeing I have a 3D object of the sofa. I place it there. Now, if I move my camera off, the sofa should remain as though it is actually there. Right? So we are augmenting reality with 3D objects. Okay? What are some applications of that? Where have you seen that we use? Games.
Glass.
To some degree.
Google Glass was a
Google Glass is another. Okay.
Emoji that they have released right now.
I don't know which sort of ones.
It simulates the face with some of the author. And based on the facial expression, it simulates
Emojis.
Education.
What education?
You can simulate planets.
You could, yeah. You can look through the view and you can see a planet.
common for this.
Common for this is
And I mean, yeah, that we have provision. I mean, you can see 3D view of
that is different, right? That is the one I spoke about earlier, where you need stitch up a panorama, a spherical panorama stitching, and then you are having the ability to move that forward. It's different from augmenting a digital object in the real world, right?
An augmented game of Mario was created.
Right. What is that game called?
Pokemon.
Pokemon, right? Pokemon is using augmented reality. And another example is, which is maybe not very obvious, people might call it visual reality also, is movies, right? To augment all sorts of objects into real world scenes, right? And that's another place where you see that. Not exactly augmented in the sense that there's maybe reflex and other things apply to make it more real. It's not exactly lifetime, real-time augmentation. And even we had worked at some point on that where we're trying to do, for example, furniture. We want to see how that works. Now, what is the intuition behind it? How does that work? The intuition behind how that works. Not the technique, right? What is the intuition of doing that work?
Basically, constructing a 3D object.
Let's say I have a 3D object. Now what do I do? How do I make it look as though, because my camera view says 2D, right? So how do I make a 3D object? I feel like it's a 3D object. What's the intuition? Not the exact technique.
So the depth of generally in 2D whatever is back. We can show the depth of the object.
So, right. So it's not just the depth alone. Right? Maybe one thing you want to make sure perspective is another perspective on the object. But other than that, what else would you need to make it a real augmented reality? What makes an augmented reality augmented reality? Okay. So what precisely make it? How do I feel that it's actually augmented?
Maybe for a regular object, if he's seeing the chair and I seeing the chair, it's the same image.
Right.
So that I need to see the change in the shape and angle.
Right. So when for any object, when I place it, as I move, my object should appear as though it is stationary with respect to that scene. Right? If I just place a 3D object here without moving it, and I just move my camera, my 3D object will be moving exactly, it will be just stationary as there, right? that won't give me the illusion of that actually the object is in the real world. Right?
Perspective transformation.
Yes, it is doing a perspective transformation, but we need to figure out that what transformation to do. Right? So if I am rotating my camera by a rotation, for example, I have to sort of move the object in the opposite direction, right? To compensate so that I get the illusion that this actually object is stationary there. So I am compensating for the rotation of my camera to make us know this object is being stationary there. So actually it's not stationary, right? I am actually just rotating this 3D object to be an illusion. Right? So what do I need? I need to figure out what I really precisely what my rotation of my camera or translation of my camera is. If I can figure that out, then I can do the rest. You have that. One example. Right? So that's another application of this. But again, this is a very hard, nasty problem. It is not being very clearly solved. So there's one way of doing this, that is what is called as marker-based augmented reality, where you print something like a marker and you use that marker to help you figure out how to place objects. If you want to do without marker with a single phone camera, it's called monocular slant, that is a very comparatively much harder problem. So you have to get an accuracy non-slant. So here we are showing you this is actually a 3D chair, and we are, well, as you can see, there is some jitter there. It's not exactly feeling as though staying there exactly. Right? Okay, so that's another. As you can see, as I'm going from the bottom, I can see as though I'm seeing on the bottom, which is what you are seeing. Alright. Alright, so that's the overview of what all can we do with this. Now let's come back. Alright, so another one is so this actually is really, you have the other one. So, given an image, a painting, Renaissance painting, can I see it as though it was a 3D scene, right? And so this is actually work of Antonio Pinesi and all, who's now at Microsoft. When we are doing work. And so here is an example of a scene that they had. It was actually just a 2D painting. Now, they make assumptions that in certain walls have planar and where they are, etc. And from a single image, they are able to reconstruct a 3D view of that image. So this is called single view reconstruction. It's search for SVRs. Good question. Any ideas? How do they form it? How do they get a depth of the image? So we'll come back. We'll come back to this. Okay, good. But, so usually we all use Euclidean geometry, right? Where you have so your angle between, for example, if you have a rectangle, angle between the sides is 90 degrees. And what are other properties can you say between? So when do we say two objects are equal under Euclidean geometry? Or what can I do to objects in Euclidean geometry? What can I do to objects in Euclidean geometry? What kind of mathematical transformations can I do? Scaling, rotational. Is scaling valid?
Distance.
What is that?
Euclidean distance.
What is that?
Euclidean distance.
Euclidean distance
Between objective.
No. So given what and so what all transform? When what is the equivalence class? under Euclidean geometry, the precise term. But okay, the gist of what I'm saying is, when do I say two objects are the same under Euclidean geometry? Right? What are the transformations I can do?
Scaling, rotation, and field transformation.
Do I see the equal official?
Maybe you can bring back the next.
Okay, that's a different transformation. Okay.
You mean actually, the question is simply you are asking what transformation would affect the distance between two points? Is that what you are asking?
That is
simply equating distance between them. If they're equal, so the difference might be less. If they're really equal, you take two objects, try to find out the distance between them. Then if they are less, the distance is less.
correct. So what you're saying is distance is what is preserved.
Yeah.
And so what is the transformation that I can do?
Scaling, translation,
Scaling is not true.
Rotation, translation.
Rotation and translation.
Scaling.
That is a higher, next level. It's a similar transformation. Right? So that's the next level of okay. But now can we use Euclidean geometry to see the images to represent the imaging process? Okay, some people here know about. So I'll ask others who don't know much about it. So can now we said you can use Euclidean is very helpful, right? That's why we all study all this line, correct? Come on, why is everyone? Are you lost now? Okay, anyone is lost? No, see, I mean, if you are lost, please raise your hand, okay? Because, I mean, see, one thing I learned going to grad school was this, that you should never be afraid of telling when you are stuck or when you don't know something. Because the moment you say that, you shed your ignorance and you are going ahead. The moment you're keeping your own small hole, you never improve. Okay? So don't worry about, because that moment you are losing your ignorance and you are getting better. So don't worry. Ask questions, please. Is everyone following till now?
I was late, so still trying to figure out.
Okay. So the question I'm asking is, so now we have a camera, right? And so what does the camera do? As we discussed, as he said, we have an image, we have an object which reflects light from some source, light source, into the camera, and that forms an image from a 3D object that's actually a projection into a 2D space, and that projection is what we call the image. Now the question is that process of creating an image. Okay? Can we use Euclidean geometry to represent that process? Okay. Let's see.
What I have a question there actually, I was thinking. So when we are talking about before it comes to the camera, we are saying it is a 3. We know it is a 3. It is because we can see 2 and that 3.
Right.
But when it comes to camera, it forms as a 2D. So what is missing here is that depth might be missing. How it might be missing? How it see? One thing is the 2D, the way it forms is just get the color information. Maybe based on that you form the 2D map, which is a image kind of that we capture. But how the 3D misses, the third dimension is getting missed when it comes to the.
So that is So we can think of any. So that's what we call magnetic projection. Right? So let's say I take my phone and I'm holding it this angle. I throw light from this one, and then the projection of it that it forms on the 2D surface. Right there, it is losing that information. Right?
Yeah, I mean the surface that we are showing it is a flat.
That might be the sorry. Maybe I should not make it a 3 flat surface. Let's have the surface, right? This is not flat. This is not epipoid, right?
Yeah.
Now if I take it from this angle and throw light from here, now the image it forms on the 2D surface, it loses one dimension there.
Yeah.
Right? And that is called the projection. And then we lose one dimension we lose it.
My question basically is something that they get to see when the lighting comes up. Generally, it is a color groups or something that comes to the character.
The light, the light reflected is composed of colors, which our eye has got cones and rods and cones, which understand what the colors etc. Right? Now,
is there any way that we can get the third dimension also so that
we can, right? So there's a whole area of 3D computer vision which is all related to that, but we need active sensors for it, right?
there are different
sensors, like for example, your Kinect sensor, right? Or you are in humans, what we do is we do get depth, and that's called synopsis. Right? How does synopsis work? Has anyone tried out this experiment? It's like my favorite experiment I tell everyone to try out. Put your close your one eye. Try it out. This is how you learn. Close your one eye. Okay. See your finger in front of you. Right. Now close your other eye. See your finger still. So if you just keep switching, you can see that your fingers are moving. Right. Now keep your finger further away. Now what happened there? Do you have any observation now? So when you keep it close by versus further away, what is the observation you see? Shift is more when? Is it further away? Can you check it out? When it's closer to you, right? When it's closer to you, the disparity is smaller, right? So the disparity of this one is inversely proportional to depth, okay? And that is why we have 2x. It tells me so for all my, now it's not quite true in the sense that only up to a certain distance, because your ability to resolve depth.
That gets simulated to multiple sensors. I mean, if I see the way you're saying it is explained, so assume I have two sensors now. So when I close my one sensor and the other sensor, there is a differentiation between.
Okay, so we can know that. So for example, close your one eye, put these two fingers. You cannot tell me which one is which one. We lose that information. And the thing is, up to about 5 feet, I think 5 feet or 5 meters, I forget the exact number. To that one, we are heavily reliant on our synopsis. Okay. After that, we have other cues. I use other cues like is one object occluding other thing? Is there a haze in environment? So we use other molecular cues for that estimation. But at a very short distance, it is our synopsis that helps us to figure out. For example, if I need to go and speak something here, if I didn't have synopsis, I would not be able to do that very well. It would be very hard for me to do. Okay, that's a very, very good question. So that's how we are able to understand depth. And actually, we'll talk about that, how we reconstruct using zero. Another way is to wrap up that particular aspect.
That boils down in a concept when you're saying that you have a fixed distance, you have two sensors.
We have two sensors, you find out what the disparity is.
That
inverse of that gives you depth. From that, I'm able to figure out that.
I think I have seen some literature where the single sensor itself, you get the multiple applications. There also you can find out the disparity.
So there are, what is that? That's what's called monocular cues. So use monocular cues. One cue is, for example, is one object in front of another object.
He's saying multiple frames.
Oh, multiple frames. Okay. So that is called single camera CEO, but where I move from one frame to another, and there is so we can think of this as being two cameras, but moved in time, right? In some sense.
Yeah.
So I can use that same idea in both cases.
You should know how much it moved up.
We have to do other things to figure out what that is. So we'll show another example of that. The slam technique we're talking about, we'll show an example. Okay. Other questions? So another way people do, so for example, can you since you asked the question, let me ask a question. You all know about Kinect sensor, right? What Xbox uses. Right? So if you stand in front of it, it's able to tell you how far your things are, right? How your hand is, how far your hand is. Is it close to it, is it far away? How does it do? So you said IR, okay?
It has a depth sensor which is able to reconstruct the entire.
How does that work? How does that sensor work?
Very similar to how our eyes work.
So does it have two cameras?
Yeah, I think so.
Okay. It measures fourth dimension depth. Yeah.
Third dimension.
RGB and
okay, RGB
and
and
based on that reconstruct the 3D image.
But how does it get that? How do you get the depth? How does the Kinect sensor get the depth? Ideas?
There is a grid mapping, which I think they some.
So there are two sensors. Let's forget the second sensor. Okay, that's the first version. Let's talk about the first version of this.
using two cameras, you can reconstruct.
So using two cameras, I could get got that. But is correct using two cameras? Is it doing stereopsis like we discussed now?
I think that even in UV sensor also.
What is it?
Maybe it shoots some light and
It shoots a light and
captures the time difference.
exactly right. It's for time of flight. Right? So what do I do? How do I know something is moving away from me? I throw something at it. It comes back to me, and I throw once more at it, and it comes back to me. If that thing moved away, so the things that is further away take more time to go and come back. Those things are further away from me. Right? So the time of light, the amount of time light rays takes to go, hit and come back, if that increases with respect to some baseline, that means that those things are further away. That's exactly how radar also works. Right? So the amount of time, the time of light is what I use to know that. Okay? So the first version of Kinect sensor used that idea. Okay? That is time of light. Send the pulse, look at the time it takes to come back, and then you understand what it is. But the second one used right, the grid. So which is what we call structured lighting. Okay, the idea of that is, so now I am standing in front of this projector, right? And let's imagine there is a we have a grid or something in projector. Okay. So imagine there's a grid I'm projecting, right? Now when I put a object in front of the grid, right? What happens to the grid? So that the grid deforms to the shape of the object, right? Now the question you're asking is, can I reconstruct, given this deformation of the object, given the deformation of the known grid, can I reconstruct what the depth change was? Okay, which is what the structured lighting, that's how the structured lighting sensor works. Okay, which is what I believe the new iPhone X has. If I won't verify this information, but I believe that's one of the things. So we actually build one ourselves.
I just came to know they are using structural lighting, the IR sensor, and the nano camera sensor. All these.
So they have three of them. Right? So I think I forget the details now. I read up about it. I need to refresh my mind. So this is a case where we build one, where we have a DLP projector, and with the projector we are projecting the pattern, sorry, now there's no pattern. We'll show the pattern in a moment. So now what happens is you essentially project patterns of varying sizes, and from that variation of pattern projection, we can reconstruct this one. The math I need to go into more details, and finally you get the depth, and then you create that as a 3D point cloud, and then you can do things with that. In this particular application, as you were saying, we want to very precisely measure how much that surface is. Right? So in that case, we want to measure within few hundreds of micron. Our accuracy has to be within 100 micron. So that's very, very precise to get that. But again, it's only a small area of the measurement, that's what I used to say. But you can actually very, very accuracy with those kinds of things.
Can we do from the smartphone camera?
No. So you need a projector for that, for this particular.
Even this projector is there, but can that software finally run on the smartphone camera?
Oh, the algorithm could potentially run, right? If it's, I mean, the algorithm for reconstructing, estimating the depth and reconstructing this one. You can write in C++. Oh, yeah, it should be able to do that. That's good.
It will take too much of time.
It will take some
It
time.
will not be an instant.
It's not instant. Okay? Alright. So, I'll keep moving. So, alright, we need to big diagram. But, alright, so coming back, right? So now, let's come back to we forget the 3D sensors, we forget stereo cameras, this has single camera. We have object which is reflecting light into my eye. Now the 3D object that is reflecting light into my eye is becoming a 2D projected image. Now the question is, for that process, can we use Euclidean geometry to represent that? Right? Anyone? So I'll give you a clue here. Okay, that is, this is a projective. This is the image of the projective using Projective Geometry. Right? Well, how would this have looked like? This using Euclidean Geometry. the railway lines will be parallel. Okay. So one struggle to this question, I was always wondering. My brain was, why did nature use Projective Geometry in the first place? why did it need to use projective geometry? Why not use Euclidean to my eye? And then I had them in my case.
That's how our biology is like. That's how I.
Why is that?
Otherwise, we cannot know the or the object is all these things.
I mean, so sure. We need projective geometry to represent. Yeah, we need that to represent the images, but
That it could be like since Euclidean cannot capture the scale.
So yes, projective helps us to understand the scale. Right? That has actually happened in Renaissance painting. So I think 15th century or so, they were still painting with Euclidean geometry, and the moment they shifted, you could see how much more real the images looked. Right? So the paintings with Euclidean geometry, where they were not assuming the perspective, it was very different from the painting the moment they used perspective. But why are we having perspective? So what you're saying is because that is not there, we don't see it as good, right? But why do I? So one is yes, we get the depth, feeling of depth, right? Anything else? Okay, I'll leave a question with everyone. Think about it during your break, and we'll come back. Okay. But anyway, so we need projective geometry to model our process of image formation.
So the other way might be we can see at one angle. Right? If we don't have if it is Euclidean, we can see at one angle. If it is projective, then we can see from all 360 degrees. I mean any object if you see.
So essentially what I'm doing, one thing I'm doing is I'm going from one dimension to a lower dimension, right? So I'm going to store this into a planar surface. So I got an Euclidean projection, right? But what problem that causes if I did only Euclidean? Relative size. I cannot. I need a big. The frame size I can store the world in is as big as the real object it is, right? My eyes are not that big, which is why I need a lens to reduce the shape size. Right? Okay. Alright. And it's just fascinating, right? How biology figured out all these things, and how it does all these things, and certain.
One thing I feel actually is if you do that way, actually there are many possibilities, right? You could do this way or this way, this way.
Right.
All the possibilities are there.
You can ask a lot of questions, yes.
Yeah,
yes.
but with the there are many possibilities to do. We don't know which to be taken.
Right. We will. Yeah, that's a very good question. I don't necessarily have a full definition.
Yeah, I can go this way. I can go make it this way or this way.
We'll take something. That's a very interesting question. So. You can just keep moving. Alright, so now one of the things, one of the problems that we have with our Cartesian coordinate system is this that, so if I have lines, right, so how do I represent, what's the equation for a line? Y is equal to C, right? Now, how can I represent a vertical line with that equation? No, but by this, what is there a problem there? What is n here? So, yeah, what is the n for this particular line? Infinity, right? Now that will cause a problem for us now, right? If I want to do any operations with my slope and the intercept, I have a problem there, right? Okay, you all see the problem? Because the moment I have infinity, now I cannot do any operations that I usually do, right? So the question then is what can we do? One thing we can do is have ideas on how can we resolve this. You all know, you all have learned this probably in college or school or whatever. What other representation can I use?
Transform an object.
What is that?
You transform the coordinates in object.
What coordinate system can you use instead? Polar. Okay, that's good. So polar coordinate would be something like this, right? X cos theta plus y sin theta equal to rho, right? So where rho is essentially the distance from this is rho, and the angle of that line is the theta, right? The problem with this is it is non-linear, right? We have a constant sign delay, which means that the linear algebra that we developed, we don't utilize that for large purposes, right? So that's what sort of messy. So one of the things you can do is what's called homogeneous representation. Okay? So where for in a 2D plane itself, I will represent my homogeneous coordinates representation of a point would be x, y, k, for example. Okay? So the idea of x, y, k is this that okay, I have any ideas now? What are we doing there? So let's say I put 1, for example, right? Okay. And this it's just very similar to then my already notation. Okay, you can imagine if I just remove that part, it's just my Euclidean, my Cartesian coordinates.
Here we are assuming the z is
Right. So it's not the third dimension really, right? So we only have 2 dimensions here. Right? We are representing with the extra value, and what that allows us to do, and keep it clean, is that it allows me. I think that all that you talked about. Yeah, I think I will.
So yeah, basically we are trying with like right now, as Sumod explained, we have problem with representing images with the regular or Euclidean geometry. So we are going with a space model where we call it as projective geometry, which particularly uses homogeneous coordinates in order to represent. So basically, as earlier image we saw, there is like railway track which was meeting at infinite place. So you can see that in the image, that infinite thing you can actually represent in the image. But can you represent it with like our Cartesian coordinate? We cannot, right? So it
will have infinity symbols,
yeah,
which will mess up, because anytime we have infinity symbol, we cannot do much with that. Right?
Yeah.
And then you have to create edge cases and edge cases on top of edge cases, etc. So can we do that cleanly?
Yeah, is my question. So, but using with homogeneous coordinate, we can. It will become kind of finite representation for the infinite point. So that's basically I'm starting here with what it is, like what homogeneous coordinate system is. So in this coordinate system, we represent a line with the form of like ax plus by plus c is equal to 0. So with this you can represent any line, and also it is interchangeable. As in, let's say. We will see. So this is my one of the line equation. This is very similar to if I multiply with a constant. This is like, so this homogeneous representation, it's here, and in the second line you can say this is equivalence to this. So homogeneous coordinates, it's representing an equivalence relation between the two lines. So all this set of like basically okay, this is for line. So for point, let's say I have a actual point as like x and y. So that will be in homogeneous systems. It will be represented by x, y, and k. K can be any constant, a real number.
Now we'll talk about k in a moment. Okay, so just hold it for a moment. Don't worry what k is. We'll show you why k is needed. Okay.
So basically, yeah, that is for points. So still, even though I represent it with 3 coordinates, so 3 numbers, still it degrees of freedom are still 2 in the homogeneous coordinate system.
point lengths.
Sorry, this one is it?
No, the last one.
Oh, okay, okay.
That's okay.
I think it will, okay. Yeah. So, like let's say in this line, if I want to have a point P, then it should satisfy the equation L transpose into x equal to 0, where L is my line represented as like A, comma B, comma C, and x is like x, y, and k. So then this point I would say that is laying on this line. So that's just equation of line. Then intersection of lines actually give us a point. I think that is our basic you all know about. And then line joining 2 points. So like let's say I have 2 points. I want to get a line joining those 2 points. I need to do a cross product. So this is just explaining the definitions of how I can get it. Okay. Then like I was just mentioning, right? Like if line 2 lines are parallel and they meet at infinity, so that is not able to represent with Euclidean geometry. I'm taking an example of 2 parallel lines here. Let's say my 2 parallel lines would be A, B, C and A, B, C dash. So you can see the image here. That will be like 2 lines with 2 different C values. When I do a cross product, what I get is B minus A into 0.
Yeah, but that's the derivation you're showing. So you can
Yeah.
just draw the lines and then see that.
How? It's in projective, right?
No, you can just say that it meets it.
Okay, yeah. So basically, as you can, you saw that it will meet at infinity. So one thing I didn't mention was when I want to transfer from homogeneous to inhomogeneous coordinate, I need to divide it by k. Divide the actual coordinates by k. So that will be like x by k and y by k. So by that definition, I am saying this point as you will get as infinite comma infinity, which is like representing a point of infinity.
So can you just maybe show that examples? Show them in homogeneous and in homogeneous. Show some points. Okay. In both the examples. Homogeneous. So for example, let's say I have here. Let's say I have point 1, 2. Okay. This is my inhomogeneous coordinates. Okay. And if I want to put it in homogeneous coordinates, then what do? I can give, for example, 1, 2, 1. Right? We are not in 3D, okay? We are in 2D only. Okay? Now instead if I gave, let's say if I gave you something like 1, 2, 2, what would that be in homogeneous coordinates?
0.5.
So 1 by 2, 1. Right? Now if I let's say draw a line from let's say this guy to that, okay, and if I put this one, where would this point would be on that line, right? So 1, 2, 1 and 1, 2, 2, all of them lie in the same line, right? Now the whole idea here is that I might have parallel lines like these, okay, and these parallel lines meet at infinity, okay. Now how do I represent that point at infinity? So I don't do that with my normal coordinates, right? Which is why we have included this homogeneous coordinates. How can I represent that? Any idea?
K equal to 0.
K equal to 0, right? So if I gave 1, 2, 0, that is the point, okay, corresponding to in this direction where the lines meet at infinity. Okay. So for this direction, I got, let's say, this is an infinite point there. Okay. Now for the next direction, I get another point. Okay. So I get another point, and so on and so forth. Right. So all the set of the locus of all these points at infinity is what is called a line at infinity. Okay. Is that clear? So I got these lines in one direction, they meet at infinity. I got the next one, they meet at infinity, and so on and so forth. The locus of all those points together, we call it line at infinity. Right? And what is equal here? Line at infinity feels like a circle. Okay? Okay. So now things are going to get a little wider, but that's okay, right? Alright.
So that line at infinity is actually represented by 0, 0, and 3.
Okay. Now we'll say why we need all this, okay? They all have importance for us. We are building up things, okay?
Okay. So in homogeneous coordinate system, so we have something called duality principle, where to any algorithm, if I replace the line by point, it's still a valid algorithm.
Right. Any statement is a valid statement.
Valid statement.
Replace the point with line. Okay. And also you can see how do you represent points and lines. Can you show that as well? Yeah, homogeneous.
Yeah. Line was like something like A, B, C transpose, and point was X, Y, K. So it is both are same.
They are very similar in the representation, right? So one of the outcomes is that there is a duality between line and point. Okay, so I can replace each other and still have statement that are true. Okay.
So yeah, that as Sumod was giving introduction regarding image formation in our eyes. So we present a very simple pinhole camera model, and we try to study how that happens and what is the math behind that. So here, this is like you can consider it as a cube with a very tiny hole, like a pinhole. So if you try to image with that hole, then you will get an actually a kind of a lens effect, and this forms an inverted image. This actually you can try out also. So this is called a pinhole. So what it is doing is converting our 3D world coordinates into a 2D image plane.
So that is the simplest camera we can create.
Yeah.
Okay.
Yeah, that is the simplest camera we can create. So so that I'm okay. Further, this I'm representing and like I'm kind of moving it, turning it around, and putting it in the same direction as here. This is my object and this is my image. So this is to further like reduce the like how we go about deriving the relations. So I'm just representing it another way. The image formation in the perspective plane. So I'll just do one more.
So let's say now I have my person standing, okay, and I have my pinhole, and let's say the rays are falling to them. So you have, okay, the person formed, right? Now, what can we say about, let's say let's say this is capital X, okay, and this is capital Z. This is small x and this is small z. What can you say about capital X, capital Z, small x and small z?
Capital X by capital Z is equal to small x by
Right. Okay. So from this now I can, so if I knew what was the size of the person and I knew what z and small z were, I could have estimated the size of the person. Right? And this is the simplest model of camera. Okay? Now we will do, so what we're doing is we are making slightly more and more complex cameras. Okay? Alright.
Yeah, this is just giving an overview of the different transformations we have in the projective geometry. So the one just you saw where I form an image of a 3D into a 2D plane, that is called as a projective transformation. That involves like rotations, translations, scaling. So together it has 8 degrees of freedom. That is the highest form.
It starts from the lowest.
Yes. Okay, so
we are also, just for your information, we are taking this workshop in a couple of weeks. So it's also a preparation for both of us to know how we want to go about it. So sorry about making you all guinea pigs on this.
So yeah, in case of Euclidean geometry, we can have just the rotation and the translation. So that's what we can mostly do in Euclidean.
So I mean, any geometry, what you're saying, geometry is where there's some invariance, right? Some certain properties have not changed, right? So what is a property that doesn't change in each of them, right? So what is the property that does not change in this particular in Euclidean? So length and areas, for example, does not change, right? Or the distance between points don't change. Okay. Now in similarity, what is the next thing that we can do? Right? So I have an object like this. Now I said all I can do is I can do this, or I can move it. What's another thing you can do now on this? So at any point, so what I said is, okay, earlier in Euclidean geometry, what I say is equivalent. Okay, is when if I only did rotation and translation, then they are equivalent. Okay. Now what is another transformation, another geometry where I can say equivalence is slightly bigger than this one. I can do slightly bigger or better, another more complex operation. What be another complex operation you can think of? What is that? Scale. Right? I stretch it in one direction, for example, right? Or I stretch in another direction, right? So I'm saying that, okay, I will say this paper is the same if this paper has only increase in length, right, or increase in width. Otherwise, it's not the same. So Euclidean geometry, it was same only if I rotated it and I translated it. But under similarity geometry, I say that it will be the same even if I stretch it a little bit. Okay, not a little bit, any amount. I don't really care, right? Okay. So what is preserved there? The invariance there is the ratio of length and angles, right? So the ratio of length, this one bit by this, that doesn't change, right? And the angle between them also, so 90 degrees is still 90 degrees. If I change that, then they are not equal. Okay. Now next one.
Yeah, next one is affine, where I not only scale, like it will be skewed also. Like I can skew it.
So I can stretch the paper in this direction, make it a trapezoid, right? And that will be the next transformation. Okay.
Yeah, the scaling will be.
So I am saying I am defining what same is. Okay. My same in Euclidean geometry was if it is only the same thing under a rotation or translation. Under similarity geometry, what I meant by same was when I did that and stretching. Now in affine transformation, I am saying what is same is all of this plus me changing it even if this is Q1.
Yeah, it's just a skew. So it will be like, it may add a same scaling, like in case of similarity, you have the same scaling in both x and y. But in case of the affine, you may have a different scaling in x and y. So that will give you a skew effect. So that will.
The difference between the scaling happens with similarity and affine.
So one is, for example, in this case, right? I had if I made a trapezoid, right? My angles are going to change now. They are no longer 90
in
degrees.
this thing, parallelism.
Yeah, parallelism is the only thing that's there. So it will be still parallel. It will be still parallel, but my angles now would change. Right? So I'm giving up more freedom here. Right? I'm making it more general. Right? And further above than that is what is called projective. Right? Where most of these things don't match. The only things that are remaining are types. That is, points will remain points, lines will remain lines, and the cross ratio will be maintained.
Something called cross ratio.
That is maintained. We'll worry about what that is. Right? So essentially now I can make lines that are not parallel. That were parallel to actually meet. That is why we couldn't. Our railway line is causing problems for us, right? Because only projective can actually make parallel lines meet. Right? We need a transformation that can convert, that will make us feel that things that are parallel would actually converge. Only then we get the perspective here. Okay?
Yeah, so we are just defining the equations here. So here in the case of Euclidean, I have an input point in the
so this to give you intuition now, just tell you the math behind it, right?
Yeah.
It's not really complicated. It just look complicated in the equation form, but it's really simple. Okay.
So you have this first four cos theta, sin theta.
That part.
Yeah, this is just a rotation part of it, if that again depends upon the value of E. Okay. And Tx, Ty are the translations. So when you transform one point in homogeneous to another, so what you will get is the rotation plus translation.
So we ask a question now, for example, right? I moved my object, we are back in Euclidean again, right? I moved it from here to here. What will the value of this matrix be? Tx and Ty will be something, everything else will be 0. Right? So what happens here, to be very precise, right? What we do, let's say I have coordinates here, 0, 0, 0, 1, etc. They multiply this matrix with this guy. This simple matrix multiplication that you all know about. You will get the new coordinates. That is actually after translation. Right? And if I give the value of theta here, I can get the rotation there. Okay?
So yeah, this in total has 3 degrees of freedom, as we say, as you see. So one is the rotation, how much I want to rotate, and 2 translations. So mainly the cases like pure rotation and pure translations are part of this. So invariants, as we mentioned earlier, the length, angle, and area will be the invariant properties of the geometry. Yeah, I think this is an example of that. So in the left, you can see as there is a translation by 2 plus 1. So the pole coordinate is shifted by 2 plus 1. And in second one, it is rotated by 5 degrees. This is, yeah, translation plus rotation together. So one thing here is like the order of how you transform, like either you rotate and translate is different from translate and then rotate. That matters. Like it is like similar to the matrix multiplication, you know, right? A into B is not equal to B into A.
That is a very deep question, for which we need the.
Is it given in 2D, does it
It matters, right? I think in 2D it's okay. 2D it's okay. 2D it's okay. In 3D it will correspond.
Yeah, 2D.
Yeah, in 2D it's okay. In 2D it's okay. In 3D it's not okay. Okay. And we have terms for them, but we will go to that now. So Raghu there has quite a bit of experience on that side of geometry. He did his graduate school in physics. And
yeah, one point about that was the affine geometry comes a lot in general with area of general relativity. So you ever wonder why the machine learning computer vision needs a lot of sensors and all answer to this.
the affine geometry requires tensors, which are connected to tensors, which is why we all have relation. So when you hear non-Euclidean geometry was used for, that is what Einstein needed to prove relativity. This is what they mean.
He took a course in projective geometry and that's where
And one more tidbit here. So there are 4 schools of geometry. One is called constructionist chemistry, which was led by HSM Coxeter and a bunch of people there. And if you have seen the Escher drawings and all that, have you seen those Escher paintings? Like a birds flying from one direction to another and they sort of reducing in one direction, or the tessellation and all that. Have you all seen those?
A big bird first and the small bird.
Right. You have seen those, right? I can show you. So you have seen these images, right? So all these. So all this, for example, uses projective geometry under the hood. Okay? So MC Escher spent quite a bit of time with HSM perpetrator to figure out something. Oh, sure, please. I somewhere maybe done. Can someone find it? Alright. So coming back, so this is what a lot of applications that happens. Okay, and then the last bit we were saying is, so there are different schools of thought in geometry itself. One is the constructivist school, some are called functional school, I think, where they use from functional theory perspective. There's algebraic one from France, and the last one. Okay, I put the last school, so I think I'll remember it anyway. Anyway, so this is all. A lot of this actually is based on Berkshires' work. But he wrote the book on projective geometry. But actually, that was very. It's not very practical. I mean, it's not very useful practical form. And this bunch of computation scientists called one person called Mohan. He's a guy who actually made this more palatable form. And then a whole bunch of results happened in late 90s and early 2000s. And that's when we actually made a lot of these differences. And yeah.
So next comes the similarity. So similarity, in case of similarity, as we were mentioning earlier, we will be having a parameter S, which will do the scale. So that will have a uniform scale in both x and y. So that will go to class of similarities. So there you have 4 degrees of freedom. One is scale and one rotation and 2 translations. Yeah, invariance.
So you understood that, right? Why is 4 degrees of freedom? So clear to everyone? So how many things do you need to fill up there? So in that matrix means 1, 2, 3, 4, 5, 6, right? But how many degrees of freedom is there?
4.
Why 4?
Theta, x, y.
Right? So there are only 4 things that can vary, right? Sine and cos are just off the parameter theta. Right?
So yeah, invariance in this is ratio of length, angle, and ratio of areas and parallels. So they remain same. Then comes affine. So in this case, as you can see, the first 4 parameters A11, A12, A21, and A22. So that can be chosen any values. So that will actually give the affine. So in case of, you can see in the image, there is a rotation and there is a deformation. This deformation is because of the parameter A11, A12, and A21 and A22. So together they give a skewing effect for the. In case of in this case, this is a rectangle that is skewed into deformed into another. So this has 6 degrees of freedom, 2 scales. That is like I mentioned, has a different scales in x and y, and 2 rotations. It has 1 more rotation apart from the plane, and 2 translations. So together it forms 6 degrees of freedom. So invariants in this are parallel lengths will be still parallel, and ratio of parallel lengths will be so that is like if you have 2 parallel lengths, you take a ratio, so that will still remain same. And ratio of areas is also preserved in case of affine.
So where do you see affine transformation in real life? I was thinking that's it, but no. Day-to-day life. Oh, sorry. What is that? Rotating QR codes. I'm not sure.
You generate the QR code and then rotate it.
That's just a rotation only, right? That's a Euclidean. I mean, that's also part of affine, but it's not. No?
Yeah, scale similar.
Yeah, if you have scale also, then that is it. If you have perspective, then it's not even. Then it goes out of scale. Okay, we think about that.
Then the form of was projective transformation. So in this case, you have apart from affine, you do have one more called projectivity. So that adds 2 more parameters, which will in together will have 8 degrees of freedom. So the image formation you saw, right? That is an example for projective transformation. So yeah, it preserves mainly the cross ratio of 4 points on a line. So we just it's a mathematical thing. We'll define later. So projective. So this is a hierarchy of transformations. So Euclidean. Okay, Euclidean comes oriented in the. Okay, first comes the Euclidean, then comes the similarity as we defined earlier, and then affine and projective transform. And this images below, you can see the leftmost, it is just an in the Euclidean space. And the second one, I'm guessing, this is in the affine.
The affine transformation is undergone for this one.
Yeah.
The last one
is the projective transformation.
Why is it projective? How is he able to say it's projective? I mean, even this also you can say projective, right? Is this projective? How will you raise your hand to say this is projective or not? Is this projective? Huh? Yes. How many of this is projective? Okay, some of you. I mean, it is projective in the sense that even similarity and Euclidean comes under projective, but it's not a good example of projective. Right? Why do we say that it's a good example of projective? Parallel is anything, right? It's very obvious, right? Parallel is anything. Because it's very important because you will use these ideas in order to calibrate your camera. The exact same idea you're talking about, you will use to calibrate the camera. Okay, alright.
Okay, that is a definition. So projectivity is an inevitable mapping from mapping edge from P square to itself. So this is like definition of projectivity is like it is a mapping of a point within the same projective plane where it is properties like geometric properties are still preserved. We discussed earlier. So in this case, let's say I have 3 points that are lying in the same line. If I transform it using the parameter h, then the resulting points will still stay in the same line. And just next slide we'll have that sample. This is okay. I'll come to that from plane to plane. I'll define that. So in this case, this is a projective plane, a model of a projective plane where earlier we were describing, right? So a point x here. Okay, this you can consider it as a projective plane. Okay, and my coordinates are x1 and x2. x3 is k. You can think it as a k. So this can vary across this line. So a point in projective plane actually represents a ray. If you remember earlier, I was defining point is like xyk, or in other terms x1, x2, and x3. Then this can vary. It is still the same point. So as you can see, a ray in a 3D plane or 3D geometry, when projected onto this plane, it is forming one point. So line length projected as 1 point. Then I have a line which is, let's say, I'm connecting 2 points into in a projective plane, but in actual it is an in a real world it's a plane that is projected as a line. So that's where we are actually losing one dimension. So yeah, and also we defined a point at infinity where the third term is 0. So all the points in the plane x2 and x1 are points at infinity. That's where they meet actually. And together this plane, right? I think x2 and x1 together that forms a line at infinity. Okay.
We'll do our demo and come back.
Sure. Demo of.
Okay, these ones we talked about.
I think previous one actually. Yeah. So here I'm saying a mapping between two planes. So there are two planes here. Similar, it's two projective planes. So that can be actually related with an equation, something like x dash equal to x h into x. So that h parameter we call it as homography. That relates between the two projective planes. And this.
So while he's drawing, I'll say this. So that's a problem you have to solve, right? You have to do the projective distortion, right? For example, I have taken a picture of a cap. I'm taking a picture of this paper from this angle. Now, after I run my algorithm, it should be automatically corrected as though I took it from the top. How do I do that? Right? So essentially, what is he saying? What I want to do is I have one projective plane which is where it was taken this way, and I want to translate it to as though it was straight, correct. Now, what is the transformation between this? This is that matrix H, the homography matrix. Right? Now, what I want to do is to find out that homography matrix. So, if I get that, or what do I do after that? If I get the homography matrix, others keep quiet. This side talk. What do I do if I get an H and I have the original one? And they will also keep quiet. What do I do now? I have H. I have the coordinates of each of those points here, right? And I have my matrix H, which I have somehow found out. Now to get the translated one, what do I have to do?
Divide.
Is it divide? Multiply, right? That's what we did, right? So X into this guy. And if it is the other way around, you take the inverse of it. Okay? So if you multiply by that, then you will be able to get that. This is what is now to show. So I want to go back.
I just So yeah, as he was defining, so we have this like points x dash and x are in two planes. So they are related by a matrix which is 3 by 3 cross matrix, which we call as H, that is homography. So as we were defining homogeneous coordinates, this H actually has here there are actually, you can see there are 3 plus 3, which is 9 elements. But we were defining projective geometry as having 8 degrees of freedom. Do you know where that one?
Did we get it wrong, or is it something else? What? Who lost where? Where did that one guy fall off?
Sorry? This is 1. Sort of, but yeah, I mean, what we basically do is we, in homogeneous form, this like you can maybe like divide it by h3 everywhere. This will be 1, so you have 8 degrees of freedom. So, given a set of, so since it has 8 degrees of freedom, so what you can do is
how many equations do you need now?
Yeah.
To solve that.
Yeah.
How many? 8
degrees of
Okay, so if I get 8 equations, now how can I get 8 equations? So I have given you
these 2 images.
8 coordinates. 4 corresponding points, right? So if I know 1, 2, 3, 4 and 1, 2, 3, 4, and I find which one should match to what, then I can mark this from this one to other one by solving that equation for H.
If it has to be done for a circle inside that.
For a
circle.
Circle. Okay. Then there's a problem there, right? Then we need a different transformation there, right? No, because what does our perspective transformation allow us to do?
No, you say even though here it is a circle.
Oh, you want to embed inside a circle, or you want it to be?
No. Currently, we are taking the corner of the images or the corner of an rectangular object.
Okay.
And conveniently we able to map into
Okay.
a matrix.
So let's say if I want to put
on the circle.
I want to put what's her name? I forget now. No. If I want Audrey, Hepburn. If I want to take her picture inside this region alone, okay, like this, okay, meaning the.
No, I want to correct the perspective of the circle itself.
The image itself, sir. What
There's a circle inside.
Instead of rectangle, you have a circle yourself. Okay. See, as long as you are able to know the similarity, like same points in the
corresponding between the
points, then you should be able
That's
to.
a difficult.
No, you can still do it.
We always lose circle.
No, so okay.
For circle, you need a center point, I guess.
No, it doesn't matter, right?
It doesn't matter.
As long as I'm taking from one shape to here, okay, and I get 4 points there. It can be 4 points like this.
4 points in a circle. Yeah.
Okay.
Yes.
Yeah. So these 4 points are the extrapolated point, not the exact point.
No, I mean, so what I want to do is I will take from here and I will put it here. Okay. I can either take from these points and then I say, okay, I want these points to be mapped here. Okay, and then automatically the transformation is found out, H is found out. Right? So what is, I don't remember, so I fully precise it.
Like the circle will become an eclipse on an.
Yes, it is.
It will become, right?
Become eclipse.
So let's say, okay, I took this original shape was like this circle. And I found 4 points inside that.
On the circle, maybe you can say.
No, it's just a circle. You don't have anything inside the circle.
Even on the circle, there are points.
There will be points on the circle.
Points,
also,
circle will be formed by points.
Points, right?
Yeah.
So I get 4 points on the circle. Let's see.
You need at least 4 points on the circle, and their corresponding points on the first.
And where these corresponding points should go to. Right? So if I just give these 4 points, this directly transform such a way that you will get something like that. Right?
You still require 4 corresponding points.
So 4 points is required, but that 4 points will not be the perfect point in the case of the because you have to get it extrapolated.
No.
That
You could do this way. So you have 4 points. If you take it polar coordinates, all the 4 points are different. They are different. So when you take it from the projected image, we can ellipse or any other shape, they will be different, right? The parameters will be different. So you won't have the
Sure, and complete.
we will take it off. Right?
Yeah, I mean, one thing I can say is like here itself, right? If you see these points are not on a same plane or not in a rectangle, right? These are still projected here, right?
Correctly, right?
Yeah, because you have the perspective transfer of the original one, so that you just apply this.
So
yeah.
I mean, so here
This
is
is what
4 points.
you have
It
H.
does not have to be. Okay, sorry. It does not have to be like a. It can be like this also. It doesn't have to be rectangular. I just need 4 points corresponding from here to here. That's all I need.
Yes.
I think the confusion comes from mentally you can map you can twist the rectangle and you can form the image, but for circle it's different. I think
It's just a mental block. That's what we see.
Visualize the problem, but when you do the math,
It's the same.
Okay.
Basically, once you get the H right, you can transform all the points. So that will give you a circle can be turned into a conic.
So what is my experience is that if I take I am able to take the point and I am able to do the perspective, everything is fine. But when I do the precision measurement, then it only happens if I on that particularly if I put an sliding outside one rectangle, then my measurements are.
Oh, so what? Okay, I know what you're saying. What you're saying is you want to transform from one circle to another bigger circle, for example. And when you do the computation, the homography might not be so precise enough. You might have a numerical error. That actually circle become ellipse. Is that the problem you see?
Kind of that.
So that is actually numerical computation problem.
but what is after you're telling that
No, his circle might not be exactly what you are saying. So
but if you calculate the distance in homogeneous the constant
As
So
long
what
as
we
he
have
has
to
a
do
constant
is what we do is that we take the center point of the circle.
We take it off.
There was another option. We take it off.
we take a break now, right? It's on full 40.
Yeah.
We'll take a small break for 5 minutes and
Shouldn't be going there. Three should be can be going, but three shouldn't be. Two is but if you are really near,
It is near
the
the
image will be.
Still we have less information, that's all. Still we can have more information. If you
No,
could
the effect of projection that you try to model it, that will be less.
how much information we get this research.
Yeah, as long as they are distributed, it is good.
So you are finding years and
Sumod.
this stuff is actually kilo.
So this is how we are going to do this.
For that,
But they are not straight for you are moving.
to do acceleration, you don't need physics geometry, which means that I can give you that one effect, right? One dots on one lines. You don't need physics geometry. But there are places you can do, for example, long distance. Then you need that is one of the questions.
And how far away the truck is conducted.
Distance more you can calculate. So people who is so other things are more we do. We have slice manufacturers
I spoke a few years back. I lost it.
They're usually sold to indicators. So there's indicators so you want what's called organization. So you want but otherwise we need to expand to I didn't show an example of how to do it. Yeah, single line.
Plan trees will augmented science. There's a range of functions. You have a manufacturing plant.
You just have a level you're trying to keep, you build the device with it, and then you walk out. The device I need to right now it's kind of like high if you go, it's more to the right if you go right now it is already on a small computer, which we have embedded which is a backpack for a normal answers where you can it's a small hologram kind of thing. So that's the basic device. Right now we have some master text and also so that's good. So it's primarily how do you just how do you sign an appointment? So what happens is it can even detect that there is a quality problem. So when the as a material from where the vision is so good that we can get this one if the camera is closed, we start feeling all the light. So when the camera is closed, all the points are exploring here. One plane
You want to talk about coordinates.
Horizon of this.
You want to talk about absolute coordinates.
Absolute coordinates. Now itself is going about. Actually, there is one thing and then something. 3D, plates, 3 plates. That road that comes to that see one particular case will show the last column is no, the last could be minus 1 also. Last column could be minus 1.
People put that as infinity. That's true, you guys. No student shoots. In probably is probably always this point gives that's only forbidden point.
You can still find the same language.
Don't do that.
That's just one input.
He gives it duality. Yeah, so
What do you mean with
you said you're absolutely taking that. Most people they demarcate this you have to short and say whatever, but as a I don't think that's very so it's a good thing. It's very good, it's very hard. But like I think if you don't have my structure, no, true. I don't disagree. The problem is how to remember all these things. That's the reason why I'm saying. Yeah. So it's this is artificial construction. That's about when you reload them. Real estate website shows moving
Actually, it's not a circle. Take the center and you draw.
Alright, so we will start here. So as we said, one of the things you want to do is, as robot is, you have a robot is moving around, you want to know the localized where it is. Right? So one of these algorithms that came up in the last couple of years, one is called ORB scan, where ORB is this particular feature detection technique in computer vision. Essentially means it's given an image to find certain important distinguishable features, that is, and one particular algorithm is called ORB. Let's forget about what the details of it is. And then what we want to do is, so these essentially finds important, interesting points in the given image. Okay? And now what you do is, you want to somehow figure out how the camera, how the robot or the person with the camera is moving around, and you want to map that and keep track of the map of how he moved around. Okay? So for example, what could this be used for? Your robot, and I want to go from here to here, and you have maybe a virtual map of what it is, and then say to go from here to here. But actually, the real world, there might be things moving around. There might be someone who put in new stuff in between, etc. So I might be detecting obstacles and all that. Let's forget that for now. But at least the very minimum thing I have to do is go from here to there. Right? Now, how do I know that how much distance I have moved in that map with respect to the real world? Right? One thing I can do is I can put some encoders on my wheels, see how much my wheel has moved, and then use that to say that. But let's assume that's not the case. I don't have that information. Okay? Or let's say I have a drone that is flying around. Right? I don't have any way of measuring how much I have moved. Right? How do I do that is what this is doing. So, it's already playing. Sorry. So, as you can see, as it moved there, each time the frame was captured. Yeah. I clear the running cost. That's okay. You can talk about it. I will.
So the idea is like we have, as I think mentioning earlier, like with stereo we can do, and this is a quite similar technique wherein you have a single camera and you have a couple of frames of that same camera. So as you move around, right, you want to basically find the similarities between two images and map them, the similarities, and we compute kind of a transformation that gives me that transforms me from one image to another, which that transformation, that value we call, something called as fundamental units, we will learn about it in the coming session. So that will actually, you can decompose it into the camera's transformation or camera matrix.
Move the picture upwards.
As in the pose of the camera. So I have, say, I started from 0, 0, 0. What is my current position? So that singularities will give me that info. And once I have that, then what is my current position in the next frame? So this keep happening for several number of frames, and those set of frames will combine together. And here, actually, okay, as you can see, these green boxes are the points that we are keeping track of when we go from one frame to another frame. So once I find a new position, I can actually kind of triangulate these points from the image into a 3D world coordinate. As you can see there, the red dots, it's a sparse reconstruction. You may not be able to see the complete 3D world, but it's very sparse. Wherever there is a key points, and like
So I can rotate here, for example, or I can move between that.
you can disable follow camera.
So as you see now, as you can see that this green thing is the current camera position, right? So and at every point it's showing that blue stopping where the camera each frame was captured.
Yeah,
So
those
that path that it's moving through is that path how the camera moves. Okay, in the 3D. So this actually is a 3D sort of a is a 3D it is a 3D view of that world. How do I rotate? So as you can see now, I can see that from different views, right, of that same scene, right. So now my algorithm is understanding how the camera is moving, right. So if I move from here to here, I know that's a rotation, right. But my algorithm has to figure out that from here to here was actually a rotation. So if we figure that out, next frame it again maybe it moves some other one. It will maybe it actually say rotation and translation. So algorithm will figure out okay actually rotation and translation, right, and so on and so forth. Okay. But initially we have, as we said, there's some few things we have to calculate for it, etc. And then we do this calculation, updation of this, the rotation and translation. Right? And that is how now we talk about rotation, translation, and what are the intrinsic. So this rotation translation forms the what is called extrinsic parameters. So a camera, so we have got three parts of the camera, right? One is the camera's body, the other is a lens and a sensor. Right? Now we can model all of these things. So the camera's body itself I can rotate or translate it. Right? That is the extrinsic parameters. And I have intrinsic parameters, which includes the lenses parameters and the sensors parameters. Now what do I want to do at any point if I want to calibrate the camera? Meaning I take a picture in the real world and I want to know how much is the distance in the actual. I take a picture of it. Now I know I can measure in the pixels how much distance is in terms of pixels in that image. But I want to know how much is that in the real world. Right? What do I need? I need these matrices that we talked about now. Right? That is one is the extrinsic matrix and the intrinsic matrix. If I have those, then I can actually go back and calculate corresponding to few pixels what actually it is in the real world. So if I calibrate my camera, I can do a lot more things. Right? Or I can do things like these also. Right? Where I can know how my camera moves. Okay? That's what we will talk about now. What are the matrices in the camera? And we have created all the things we needed now in terms of projective geometry to talk about it. Now we will talk about what those things are and how we are going to how we can calibrate the camera and how we can do something like this in a very quick session. Okay?
Yeah, so these are some more examples of the projective transformation itself. So as you can see here, a house, when this is a shadow of a house with respect to sun. So that is a projective transformation, as you see in the real life. And in the other first image, you can see you have two cameras and you are looking at the same scene. So basically, you have two projective transformations in two cameras, but still those two are related by another another relation with rotation and translation. And third one is like.
Is that always correct? Can I say that one camera to other camera, there's only rotation and translation? Is that true?
If they're on the same line, so
Okay, let's forget that part for now. Anything else? So I got my iPhone and I got his iPhone. Okay, and then we are going to take photos from two different angles. Okay. Now, if I see an image, can I say that with this rotational translation, I can create this one image to the other image, or do I need anything more?
calibration.
What calibration? So, what calibration do I need?
The focus.
So the lens, the effects of lens. Now, what I said is, remember the body of the camera and the lens and the image sensor, right? So now all I told you by rotation is that I rotated this guy from here to here, right? So most likely, so that rotation has been taken care of, but the sensor, because maybe from the same sensor, same manufacturer, always sensor is the same. But the other part, lens part, that will not be exactly the same, right? Okay, so that may be another thing I need to then account for. Okay. Now, if it's the same camera from these two positions, then it's only rotation.
I think it is in the C. The third image where the same camera is rotated about its axis. So it's a pure rotation. So next. Okay. So this is okay. Earlier we represented a point at infinity, line at infinity, right? So what is the effect of affine transformation or the projective transformation on these? So as you can see, like in the first slide, right, A into T, 0 and V. So this is it's supposed to be 1 actually. So that is this is an affine transformation. So x1 and x2 0 is a point at infinity, as we defined earlier, right? So if I have the affine transformation for that point, it will be still point at infinity. But whereas if you take the projective transform, which has the projective parts also, v of t and v. So in this case, that point at infinity will become finite. So that is what actually describes the image of a camera. So you can still able to image it within the camera.
Yeah, I can just talk one bit.
Yeah, okay. Next is
I can start with this.
Yeah. Okay. So basically, this projective transformation actually can be decomposed into multiple matrices. So that is like H is a projective transformation which can be decomposed into similarity transformation and just the affine. We won't take care of rotation and scale. That is already taken care in case of similarity. And affine just has K with 4 values, and then the projective which is just V. So together that forms a complete projective transformation. This decomposition will help in like further how we are trying to estimate the like camera pose with the as we described like slant, right? So how we can recover that camera matrices. So this decomposition will help in that. So this is an example below. So where H is an projective transformation matrix, and that is decomposed into 3 individual like similarity, affine, and then the projective transform. Okay. Yeah. Next, I think it's
Continue.
So yeah, we'll again come back to camera model and how we can calibrate. As Sumod was explaining, we'll have different parameters of the camera. So we'll just go in a little bit detail about how we are going to do that. So okay, just I'll use this itself. So in this case, earlier, if you see, I'm mapping a point A in the real world, which is x, y, z, onto the projective plane, which is a small a, x, comma, y, comma, f. where f is the focal length. That's where our normal image formation happens, right? If you remember thin lens model, like you have a angle. So
it's a nice, slightly bigger, more complex camera from instead of the pinhole camera, right?
So, so this length will be f actually, where the image formed. So that is the state x, y, x comma y comma f, and so that is in the image plane. And point P, which is the center of that image plane, is called as principal point, and the camera center is actually at C. Okay. So, like let's say I take a cross section of plane x and z, sorry y and z. If I take a cross section vertically with respect to plane x and y and z, this is what I get, right? So I have f, then this height will be like, okay, that's what we are going to calculate, right? So I'm trying to calculate a height, or angle ACZ. So that will be like, tan of ACZ will be y by f.
So this is the same thing that we spoke about earlier, right?
Yeah.
Where instead of using symmetric triangles, we get that one. And that's the very same thing that we get in here.
Both x and y, you actually get a
So
relation.
earlier I just showed you in the case of x alone, but I can this actually we can talk about in the case of x and y. But you remember the equation we wrote, x by capital Z, x by capital Z equal to small x by small z, right? So instead of the capital Z, we have f, okay, focal length, which is giving meaning to them, right? Okay. So now we got those two equations.
Yeah. So it's okay. So another one thing we want to consider here is we just consider a camera, but our camera pixels, it will have a, like the image sensor will have multiple pixels on which the image is formed. So that pixel size can be, that pixel shape can be of maybe a square or a skewed rectangle, something like that. So if I assume that is not a perfect square, then I will have a parameter something called mx and my. That are the scaling factors that will actually affect the image formation of my camera. So that's what I am adding it here, and together I am calling it as u and v instead of x, small x and small y. Okay. Then apart from this, in the previous image I was in the previous image the coordinate center was somewhere else, but actual camera center will be the center of the image plane. So I will consider that as Cx and Cy. So that factor I am adding it here. So mx plus f is alpha x, and my plus f is alpha y. So together that u v will be, this will be the new equation for my image coordinate u and v. Let's see. Okay. So together all this alpha x and alpha y and Cx and Cy, those together form a something called intrinsic parameters of the camera. So how we can model that is that u v w equal to alpha x 0 0 alpha y 0 0 and Cx and Cy. So these are called intrinsic parameters of the camera, and still our xc and yc and zc are with respect to the camera center, they are in the camera coordinate system. We are still not into the world coordinate system. Okay. So yeah, that is this is actually this alpha x, alpha y, cx, cy together actually has 5 degrees of freedom. So this is where actually we want to explain that 5 degrees of freedom.
Yeah. Go to or you go ahead.
Sure.
Oh, actually no, I'll CXUI is the offset, right? From the center.
Camera center. That is the principal point. So,
So, as you all see now, this is the same one he just explained. So we got the similarity, and then he spoke about the camera projection matrix. Then just skip over, and there we are. Right? So what are we trying to do? We are trying to
I have
convert.
missed one parameter. Yes, like I'm assuming my pixels are square.
So your pixel will not be square actually, right? In the camera, your pixel can be in one dimension, it might be larger than the other dimension. Right? So we need to model all these properties, right? So if they are actually equal in both dimensions, then x actually is 1.
Sorry,
0. Okay. And so then that means only the other ones I need to worry about. Okay. Now, so here what is happening? So given a coordinate so this is a world coordinate. Okay, so let's say I am measuring a point that is at so and so meter from another one, right? So I want to translate that particular point into my image coordinate, that is in terms of pixel, from the real world to the pixel coordinates. Right? This is the transformation that is undergoing. Okay, forgetting the rotation and translation for now. Okay, so all I want to know is between two. How do I translate between these two coordinate systems? Right, and px and pi and you call cx.
Yeah,
that's a principal point. And the others are now you combine them. You show that you explain.
Yeah, I had a combined one.
So he had a combined version of this matrix, right? So I mean, essentially what I'm saying is you can actually split. You can separate them into two matrices. One which has got the focal length that you see there. That is actually the lens matrix. Okay, so that's modeling the now. Again, our camera is still not the complicated camera that we all use, okay, which has got multiple lens elements. This is a simplified version which actually only has a thin lens model, okay, and therefore we are saying this is the equation for that, okay, and this particular one we are seeing here, this one represents the thin lens part of it, and this represents the sensor part of it, and those two combined together, okay, there is the intrinsic matrix, okay, and we also have another matrix. Not necessarily. So I can have so my focal length can vary, right? Because
Lens
depends on the lens that you're using. So that is actually a good question you're asking. So I'll show you something about that. So my focal length is going to decide how much my magnification factor is going to be. Right? Remember, as I move further away, the more magnified image I can get. Right? So my plane of imaging can go further away, and the size of that will vary based upon the focal length. Even in case of digital camera, right? If you have a lens, right, it will move the length, the lens elements will move such a way that the focal length can increase, and that is why, for example, your focal length on your camera, on your mobile phone, will be very small. There will be a very small variation it can do. Okay, but if you have a big telephoto lens like that, okay, that can have a huge impact in terms of how far you can get, right? So that's a 1200 to 1700 millimeter lens from Nikon. In that particular case, you can see those two small people there being zoomed in with that telephoto lens, right? And not only that, actually these have some other extra effects as well. So for example, one of the effects you will see is that you can see there is what is called compressed depth, okay? That is, so if I take a picture of a person, so if I want to take, for example, when I do photography, I will take a picture of a person, a portrait photo, I will ask the person to stand further away and I will take a photo from further away. What that does is it compresses the facial features in your face, thereby it gives you a better portrait picture. Okay, and an example of that.
We have a lens registration.
Yeah, I don't go to that for now. So one of those things, along with all this, they use is something called this dolly effect, which I just play. I don't know if you have seen this. You can see that for 5 seconds.
Let's see how. The dolly zoom, or sometimes called the vertigo effect, started in Hitchcock's film Vertigo in 1958. He made a smooth track and steady zoom to pull it off nicely, which is why it wasn't developed sooner. The shot is essentially an optical illusion.
Okay, I can see it here because streaming this again. So,
on the camera lens while tracking the camera forward or backward. The result is the foreground stays in the same position while the background appears to squeeze or stretch depending on which direction you go. It actually teaches you one.
So what it's doing is you're keeping the size of the one particular object fixed, and then you're changing your focal length, okay, and keeping your focus still the same focus, and thereby what effect do you get? You are able to get an effect like this, for example. So using computer vision ideas to do filmmaking, so that it actually has an impact on the person. Okay. So one quick thing I want to talk about is this. So one of the things you have seen is what we call vanishing points. Okay. So what are vanishing points? So for example, as we discussed, so lines here are meeting at infinity, right? So as you can see, these two lines meet at infinity, these two lines meet at infinity, etc. And we spoke about that those lines together, they form all those locus of all those infinity points, or ideal points, they form the line at infinity. Right? Now actually if you connect them, that actually is what we call the horizon line. Okay? So when you're taking a picture, the horizon is that level where that is equivalent, that is the picture of the line at infinity in your camera. Okay? Once we can get that line at infinity, okay, or the horizon, then we can do a lot more things with the image. Okay? Actually we can calibrate the camera even. Okay? So one way of doing that is what is called the 3 vanishing point calibration. Okay? And the idea of that is you get 3 vanishing points, and once you get there, then you can do some little bit of geometry and use that in order to actually find out the camera. So essentially, what are things you need here? One is you can find the intrinsic matrix here. Okay, that is your focal length and your center, the PC EXPY, right, principal point. You can get those. How do you get them? So the idea is that now you have these 3 points, and you should imagine like I am sort of putting a tetrahedron on top of it. Okay. Now all of these angles are 90 degrees with respect to each other, right? I'm putting that on top, and now if I get the perpendicular bisectors of those guys, that intersection point and the red line, okay, which goes from, so imagine there are 3 points here, 1, 2, 3, and I'm keeping it this way, and there's a perpendicular bisector that goes here, that guy, the length of that guy will give me the focal length. Okay, you can actually derive that. Once I get that, and I can get from, similarly I can get the principal point as well. And once I get that, then I actually I calibrate my camera, right? So, and this is the kind of techniques that we use in order to do that. So this is one way of doing it. The other way of doing it is for, I mean, this particular one happened in the case when I had 3 entry points. Okay. What if I don't have that? Right? And in that case, what we do is what is called, we have.
Yeah. So we will. I think I have to just define that.
Yeah.
So till now we were defining like the intrinsic parameters, right? So this is, as I was saying earlier, xy, xc and yc and zc are with respect to the camera coordinates. But in actual camera itself might have a rotation and translation with respect to the real world. So that transformation is like what we call extrinsic calibration of the camera, and that is very like particular to a specific pose. Like I have right now, I have a still camera here that may have a certain rotation and translation with respect to the real world. When I move it, it will have a different rotation and translation again. If I say like my origin is at the root center, root corner, then it will have a different rotation and translation with respect to that corner. So that is the that is defined as extrinsic calibration, that is rotation and translation. So input next slide.
So you are saying essentially that the camera will have a different distortion, the spherical distortion, or the
No, we are not talking about distortion here. Our camera model is still thin lens based camera.
Still thin lens.
Okay. So we are not talking about, it's just about, we are saying if a camera was originally here and it moved here, what is the rotation and translation that I want to understand what transformation has undergone. Okay. Which is what we are trying to compute.
Yeah, for example, PW in world coordinates, for example, certain point here with respect to world coordinates. If I right now I had defined it as here this xy, xc, yc, zc is a PC, that is point in camera coordinate system. So this PC is in camera coordinate. So in order to get the real world coordinate with respect to the world, then I have the rotation and translation. So that is modeled as R into PW plus T. Okay. So that I can write in homogeneous transform as PC. Okay. Yeah, as in the equation 2. So PC1 equal to R into T into PW by 1. So this is called as R and T are called as extrinsic calibration or extrinsic parameters of the camera. Okay. So application of homology. We have that next slide. So here I'm saying what are the different kinds of lens effect you can have. So this is okay. The one here you see is a radial distortion. And that maybe have either like inwards or outwards. If you can see a CRT old monitors, right, where you have a dome shape. So there it is a kind of such a distortion we have with respect to the lens. And tangential distortion may be like if my lens elements are not like parallel perpendicular to the principal axis, then you may have something called a tangential distortion. This is like to model the lens for the camera calibration.
So
as Sumod was earlier explaining the matrix, right, which is like f 0, 0, f 0, 0, 0, 1. So this is like with respect to the thin lens. So in these cases, these will have some other parameters that will model the effect.
So the radial distortion is inherent and tangential is the by defect.
Inherent of a particular lens type, and other one lens. Yeah. Correct. For example, if you have a wide angle lens, you will have a radial distortion. I mean, not radial, you will have a parallel distortion.
No, that is parallel. Yeah. I mean, that is still part of radial life. Tangential, yeah, maybe.
Yeah, it could be.
Defect.
Yeah, it could be defect. Yeah.
Or like maybe inconsistency in what you call it? Manufacturing.
Yeah, maybe defect. Okay. Anyway.
But that will get caught into quality test, right?
It depends on how. Yeah. So if you buy a smartphone cameras, they're probably not. It's not guaranteed in those things. If you're buying very high-end resolution cameras,
in the industrial vision, like in the industrial vision,
correct. So if you're buying machine camera, which are rated for those things, they would have those kind of guarantees, but not your iPhone camera.
And in the industrial vision, you should not have the radial as well.
So it depends. I mean, so you might. So it's going to be very hard for you to avoid radial distortion. What you will have is you will have calibration routines and procedures that you can apply to reduce the effect of that.
Yeah.
Or
you may still have it because like since the elements are still fit and they have
highly different.
So there are routines that you do. Yeah. So the picture is that. So the one model we mentioned that doesn't work for more complicated lens elements and all that. In which case you have more complicated modeling. And in our case, so we have done quite a bit of times. We have to coming up with that model itself might be very hard. Okay? But there could be problems for people spending 2 months and a couple of tens of lakhs of rupees may be worthwhile to get that very precisely because the application requires that precision. Right? In which case we will come up with that model. Okay, that is the other example.
Go to the previous surface. Previous surface. Okay. Yeah, here this is a complete equation of camera.
You can apply corrections to all these distortion.
You can, correct. You need to calibrate accordingly, and then you should have models that can capture that in order to do correctly.
So this is the complete equation of camera, like equation 3, where u, v, w is the image point in homogeneous coordinates, and x, y, z here I'm explaining a routine for calibration, so I made it as 0. But it will be actually z and 1. Then k is the intrinsic, and r and t are rotation and translation.
So you remember now, right? This is actually the four dimensions there are actually 3 dimensions of the real world because of the real world coordinate system. 1 extra dimension for the homogeneous coordinate, and it maps into 2 dimension. But the 2 dimension with the added on extra from the homogeneous, and therefore the transformation is from the 4 by 1 to a 3 by 1 vectors. Okay? And in between you have two, and you have two. You have the 2 parameters, 2 matrices. One is the extrinsic and the intrinsic. Okay.
Okay. So in this case, so what I was trying to explain here is like since I need to calibrate it, I may assume that I have certain known points within certain plane in the real world, which means the depth is not varying. Those points are within a plane, and if I know the corresponding points within the image, then I can calibrate it more easily as I remove one of the component. So that is like there are multiple ways of calibrating it. So this is one particular method which uses a 2D plane to calibrate. Like you have seen a checkerboard, right? So that can be used for calibrating the camera.
That again depends upon your application about what degree of resolution you need. Yeah. The gold standard is a 3-dimensional cube or checkerboard or some sort of known pattern. It's actually needed for very precise measurements. But up to you can use only a checkerboard of 2 dimensions where you know the exact shape to do that.
Okay. So as earlier we were defining, right, what it is actually represents. transformation from a plane in real world to the transformation of plane in an image plane. So that actually can be again related with the homography H. Right? So in which in turn is K into R and T. So basically, if you know the points in image and the world coordinates, and you can calculate the homography, which in turn can be decomposed into the intrinsic and extrinsic parameters. Yeah, this is just an overview of how it is done.
So how usually we do like calibration? I know you all are really are now over your head at the moment. We have gone over your head at the moment. But just a very quick overview of it is this that.
Yeah. So you have the object points known in the object plane, so x, y, and assume z as 0. And you know that their corresponding image points. So then you can calculate the homography using the correspondence as like 4 points or the
which we discussed about already.
Yeah, which we discussed already. And then that homography can be actually decomposed into the K, R, and T. So that is, it is in actual you may require just 4 points for calculating homography. So, but decomposing that into K, R, T, you may require more than 4 points. So, yeah, so that is how we can calculate the K and R, T. And one important factor here is like K is like constant for a camera and the lens setup that you have. So it doesn't vary if you move around the camera, unless until you disturb the lens again. That is K. So that remains constant. But if camera moves, your RLT varies.
So it will not work for the this homography will not work if I take the imaging from the remote distance.
I'm sorry?
Then this homography will whatever calibration you do, that will not be valid if I need to keep applying images from the remote distance and all.
Where I move the camera and
keep moving both of them.
yeah, if intrinsic is remain same, you still again require corresponds to calculate the other RLT. Intrinsic.
So meaning if the camera lens was not disturbed.
Camera lens is not disturbed, but my height and everything keep changing from the.
That is fine because I am only moving my I'm only changing my extrinsic parameters. I am not changing my intrinsic parameters. Okay. Now this is very usually people will say like my customer experience is this, right? They'll say no we will not touch the camera, but most of the time the intrinsic they would have done something or they would have shaken the camera enough that the lens elements move, etc. So it's very hard to give that kind of guarantees, but usually there will be some ones.
Yeah, but then this calibration is only applicable for a fixed camera system.
Yes, you can apply it for moving, but you have to move such a way that your lens is locked, etc. So that lens local, the focal length of the lens does not change at all.
The thing that I am looking for a smartphone.
It does change. It does change. I mean, your focal length of your camera changes when you take photos. Which you cannot. Then you cannot. What you're saying is lens doesn't change. The focal length doesn't change. You're locking the focal length. Okay. So we will take this off. Last. Okay. So we'll just finish with this last part. So again, we spoke about stereo, right? So we spoke about how we can get disparity.
What is the difference between fundamental matrix and
fundamental matrix and homography? So again, homography, you are saying it's a 2D homography, right? So you are transforming an image point, like points in a plane to another plane. It's still in the plane to plane. But when it comes to fundamental matrix, it is from a image to image where those points are, right, maybe like 3D points. Image points are 2D points, but the fundamental actually connects the third dimension.
The real one.
Like if you are in the image itself, if you are looking at the points that are in the same plane, then it is fine. It's still homography. But if you are looking at the third dimension,
so homography basically assumes the points are
in the same plane. Yes.
I mean, so that term is sort of abused a little bit. So that's why he said
2D homography.
So that is where we are trying to use.
homography matrix. I think if Either ransack or.
So ransack is a specific technique, randomized and consensus sampling. That's a specific technique for how do you reduce the effect of outliers.
The outliers.
So that particular case, the solving is actually just a linear algebra 2D that you're solving, right? To get that one, you're putting ransack around it. That if there are outliers, then they're not exactly correct. How do you handle them, right? But now to compute fundamental metrics, you have to do other things as well. Which I think you don't go into that details. We take it. Any other questions? So we were thinking we'll go into fundamental metrics, but I think at 10 o'clock in the morning we realized that this is just too much of stuff for us to cover, so we cannot get there today. So we would now talk about the fundamental metrics, essential metrics, and how we actually do the serious stuff. But yeah, but I think we cannot get there. Finish with the depth. So as we said, we get these two camera views, we get the disparity, and the disparity, and the inverse of the inverse of disparity, I know how far things are. Okay. Once I have that, then what can I do? Then one very quick thing I can do is I can use that depth, right, and I can reconstruct. Okay, what do? I take pixels which are at various distances, things are at further away. I have a 3D volumetric space, and in that one I put things that are further away, far away, and the close by. That way I am creating some sort of a reconstruction of the 3D scene by using this. By using this to do that. I'm giving a very representative view here now. Now, to actually do that correctly, there are a few things. One of which is fundamental metrics, or we have what is called Epipolar geometry, where these two cameras are looking at the same object, and if you have what is called rectified cameras, in which case what happens is these two lines, a particular point in one image.
You have to basically correct the translation.
Correct. I mean, there's any. So essentially, what happens is if you have the essentially one point then can actually be on will actually in the next image it will be in the same line essentially. So meaning
simple thing can be just put two images like this, draw simply blank a line. If all the points present and the same thing, just see which point falls on the line.
So it's some sort of correction whereby we ensure that the epipoles align up themselves. Okay? Yeah. And what we're doing, why is that important for me is that if I found one point and I found a new point. I found a 1 point one image, other point. I want to find the equivalent point in the other image. So let's say I got two images. I did some sort of a feature detection. I got a bunch of points here, bunch of points there. Now I want to figure out which point here matches to which point there. If I rectified them, then all I have to do is I just have to do a y-axis. I have to do a search along y-axis to find out what the equivalent point is. If it is correctly rectified. Okay? So that reduces my search in some sense, and that makes it effective for me to do that. So once I do that, then I can get, there are two kinds of disparity we get. One is called dense disparity or sparse. Sparse is when I do that for every, let's say I find out a given two images, I run some detector, I get few key points, and I only get the depth for them. Okay? But I cannot reconstruct this only based on sparse one. So if I want to do a reconstruction, then I want to I want to do a dense one, in which case we do a dense matching, okay? Where we make some assumptions about we explain about how light falls, etc. I don't know details of what stereo assumptions are, but then you essentially for every point in the new image you have two rectified images. In one image you look for other image in the same line, okay? And then you get a dense depth. Once you get that, then you can do reconstruction. Okay? That's one way of doing it. Okay? There are a couple of more ways of doing it, but for which we need to build more mathematics. Okay? So in the interest of time today, we will not go there. So Epipolar geometry again is a particular case of projective geometry, right? In the case of two cameras that are facing the same scene, right? And because of that, I can make some more assumptions on that matrix, right? And that's what essentially we're doing here. Right? So now the takeaway is this, right? Oh, we get this. Okay, as he gets to the example, I will start reviewing it. So, as we discussed, projective geometry is a more general version of geometry than Euclidean geometry, where we spoke about the hierarchy of geometries, right? Euclidean geometry, similarity, affine, and then projective. As we go more general, the definition of what saying means changes. In Euclidean, it is just rotation translation. In similarity, we can stretch them. In affine, we can skew them. And in projective, parallel lines start to meet. Which is why it's helpful for us to use that. We also spoke about how we can use projective transformations to model the imaging process of a camera. We spoke about the internal intrinsic calibration intrinsic matrices and the extrinsic matrices. We spoke about the fact that intrinsic matrix are actually what the sensor and the lens part of it, what we model, and the extrinsic is what the actual, when you rotate the camera, for example, okay? And rotational translation of the camera. And then we spoke about the fact that how once we get these, what are the different things you can do. We saw the example initially of how we can do homography or homography distortion of a given image, or for example, you have an image, you correct it, for example, what you do. Another example of that is image stitching, where given a set of images, I need to find out how to align them. Okay? So what do? I find out a whole bunch of points on each of them, and then I match them. Once I match them, then I find the transformation between each of them. Right? The homography distance. Once I get it, so yeah, here is the algorithm for that. Right? Find the homography between two of the images for each of these pairs of image. Okay. Once I find that, I do what is called Ransack technique. It's very relatively straightforward. It's nothing complicated. All I'm doing is that, so let's say I have a bunch of points. Okay. A simple, I'll say ransack for a line fitting, for example. Okay. Let's say I have a bunch of lines, a bunch of points. I want to fit a line to it. Okay. Let's say a couple of them are off the line. Okay. So what does ransack say? It says that. So what would I do if I fit a line? Maybe my lines could go to this, something like this. Okay. Which maybe is the right line. Right. The right line actually is this red line. This red line. Okay. But my fitting could be getting the wrong line potentially. Right. So how do I reduce the effect on the outliers who are potentially wrong? Meaning when I'm matching the correspondence between points, I could match them wrongly also. How do I reduce the effect of that? Right? So what randomized consensus says is that most of the people, most of these points together will give the right answer, but some of them might not give the right answer. So what do? I get each of these ones to give me a fit for the line. So I might remove one or two points, couple of points, and I'll try fitting, and I'll get one fit like this, one fit like that, etc. But now when I take a consensus amongst them, and I look at some error or so, it will tell me that, oh, you know what, most of the guys, get this part correctly. Right? Which means that that is probably the right fit for the line. Right? I can do same thing with homography also. Right? If I get few points that are outliers that are causing problem, I only take a subset of them, can compute homographies over many of them, and I see how far off these homographies are. And that error gives me an intuition about how far this is. Right? So that is essentially what we are doing inside that.
To optimize, they are using ransack.
It is to remove the effect of outliers is what we are doing using ransack. Okay? And then once we get this one, we warp it. Right? So essentially, we can do what is called a chaining of homography. So I find first with this guy, then this guy, etc. Then I have central one. So I have a bunch of homographies. I just multiply all them together with a central image, and I get the how I can match all of them. Finally, then I get these ones, and then after you can see maybe there is blending issues here. Then I do one quick blending on top of the image, and I get a nice stitch. Now, if I get a stitch like this, I can do that also for a 3D one, and we can create your own street view. Okay. With lot more other things to say that as well. Okay. Alright. So now that is another application of the projective geometry that we have seen. And other things we spoke about is again, so we use homogeneous coordinate system, which allows us to represent lines. Essentially, for example, we were having problems with the infinities. We couldn't handle them properly. And by having homogeneous coordinate, we could handle that. And we could also represent lines at infinity, meaning lines with a median at infinity by using them. Those points are called ideal points, or they are called lines at points at infinity. And the locus of all these points together forms a line. It actually looks like a circle. And that is called the line at infinity, and that actually allows us to do things in the real world. Now the horizon in the world, when you take a camera and you look at it, the horizon is actually the line that represents the line at infinity. It's a picture of the line at infinity in our current image. Okay? If I can figure that out, I can use that to calibrate my camera. Right? And so, for example, if I'm looking at my camera like this, my horizon would be at, at the middle of the image. Right? When looking at the bottom, the horizon will move up or down. Right? So the horizon has an effect in terms of how it is moving. And then anything else? And then we spoke about how we can calibrate the camera. One example we showed the 3 vanishing points what we can do using some amount of geometry. Another one using how we can use the we can use checkerboard, find the matches, and then along once you find the matches, you do what is called as you do linear, not linear, but fit. Okay, I'll come back to the phone and I'll take freeze now. You do that, and then you essentially get the you fit the matrix and you solve it. You got the calibration. Once the camera is calibrated, then I can know when I move my camera, for example, where it is moving, right? Or I can use that with my, for example, for knowing the position of once my camera moves around, right? So I can take, so if I'm a robot and I'm moving, I have a bunch of scenes and I have points of how they move. I can use these, for example, to figure out what the rotation translation is, with which I can keep track of how my robot moves. Okay. So that is projective geometry. Questions?
Image stitching.
We can show one maybe. I think we could buy the type. If you want to watch, we can show it after session. Questions? Yeah, some of you I think have questions. We will take it separately. Others? So there's the example of image stitching where you're finding the those were those. Can you put them side by side? So those were 2 of the ones, you had to stitch them together, and the algorithm found out the various different points that are matching. So the lines, these lines here are showing that this point here and that point there are the same thing, and so on and so forth. There are a bunch of matches, and then you're doing, as we said, ransack, for example, to find out the homographies, and you put ransack as well, and that ensures that it's a good, really good matches are kept, bad matches are thrown away, and then finally you get them, and then you merge them. What is that? Yeah, so. So one thing maybe I have to add here is this, that, or the reason why you're doing one is that one of the things I felt in India, so I did my grad school, I did my undergraduate